See me!
Some of us use muscles to generate extreme force, like this. Others choose to produce more delicate movements, like these. But for both the fighter and the pianist, success depends on the ability of their muscle cells to get shorter. By contracting when ordered to, muscles produce every movement in the human body. Muscle cells help us survive in a competitive world. But it isn't just brute force that helps us survive. Even if we like nothing better than to slump down and watch a good movie, we still depend on many different types of muscle cells inside us to keep us alive. Even a simple action uses many different muscles. Taking a drink uses arm muscles to lift it, throat muscles to swallow, intestinal muscles to help it on its way down the body, and bladder muscles to expel it. Some of these actions, the internal ones, are beyond our conscious control. But there are also times when we just decide to act, and the muscles do the rest.
Nice one!
There are really two groups of muscles in the human body. The ones controlling bodily activities deep inside us that we're not aware of most of the time, and the more familiar muscles that we control with our nerves, the voluntary muscles. We use our voluntary muscles for accuracy more often than strength. But when we need to, even the least fit of us can generate several pounds of force with each square inch of muscle. This means that the massive muscles at the back of the thigh, for example, can generate a tension of up to 2,000 pounds. There are about 400 individual voluntary muscles in the human body, and they have the job of resisting force as well as delivering it. With training, human muscles, like these fighters, can generate 3 times the force that most of us can manage. Even the average human packs a lot of power inside his muscles. If all the muscles in our body could pull together in the same direction at the same time, they could lift 25 tons. A muscle has one simple job: to get shorter and exert a force between 2 parts of the body. But when it does contract, a muscle still has the same volume. So while this biceps gets shorter, it also gets fatter. The biceps does its job by pulling a movable bone, the forearm, towards a fixed bone, the shoulder. The muscle is joined to these bones by tough inelastic tissue, the tendons. But before it can do anything, the muscle has to receive an instruction to contract. and that comes down a nerve fiber from the brain. At a microscopic level, the muscle is made up of millions of individual fibers, and they'll only contract when the nerve message arrives here, at these bulbous nerve endings lying on the outside of the muscle. When a nerve message arrives at the end of the nerve, it has to jump a tiny gap before it can cause the muscle to contract. The message is ferried across the gap by messenger molecules which slot into the muscle membrane. These molecules fit into the muscle membrane like a key in a lock. They cause one quick muscle contraction, and then they have to be cleared out of the way by different molecules in case another contraction is needed. Usually, the muscle fibers will contract many times a second as a succession of chemical messengers pour across the gap and get wiped away. These are just the events at any one point on a muscle. But any human action uses many muscle fibers contracting in a regular pattern. To produce strength like this, a lot of muscle fibers pull in the same direction under the control of a few nerves. In fact, there are millions of tiny contractions in the arm and the hand which add up to produce a steady force. When the body makes strong, steady movements, it uses many long muscle fibers, all moving at once, in response to one single command from the brain. But sometimes we need to move light objects with incredible speed and accuracy. Eyes, for example, and fingers. Fast movements like these are only possible because the finger muscles are small. A wave of contraction in a muscle moves at 4 or 5 feet a second. There are muscles in the body that are more than 18 inches long, in the thigh, for example. Fast, delicate movements of the legs aren't really possible when it takes a quarter of a second or more to contract. To play 2 or 3 notes in succession means sending a rapid sequence of nerve messages to muscles in the fingers, the hand, and the arm. In fact, in the part of the brain that controls our movements, there are more brain cells devoted to the fingers than to any other moving parts. How does the body organize itself to produce such a wide range of muscle activities? One nerve impulse causes many muscle cells to contract, while another triggers just 1 or 2. In fact, the links between our nerves and our muscles are like a kind of fixed wiring. A nerve and the muscle fibers it controls are together called a motor unit. In the fingers, a motor unit may be as small as 10 fibers to 1 nerve. But in the bigger muscles of the body, which need strength rather than delicacy, a motor unit may be 1 nerve controlling hundreds of muscle fibers. But what happens inside an individual muscle when it receives a nerve message telling it to contract? To find out, we need to penetrate down to the level of the individual molecules in a muscle cell. Here's a single muscle fiber, and the secret of how it shortens is hidden in these stripes that run across it. Each of them marks a tiny zone of contraction. the fibers making a series of twitches in response to a nerve signal. Each line marks the place where millions of stick-like molecules are lined up side by side. These molecules interweave with others lined up facing them. The fiber shortens when the individual pink molecules pull against blue arms that interweave among them. When the blue molecules are as close as possible to each other, the muscle is fully contracted. This can produce an overall shortening of 50% or so in a muscle like the biceps. Like climbers gripping the sides of a gully, the molecules in our muscles pull against each other to produce all our human movements. Most of the time, our muscle fibers don't all contract at once, even in a single muscle. To vary the strength of an individual muscle from moment to moment, we alter the number of fibers we bring into action at any one time. This means that even a large muscle can exert a small force. To lend a helping hand up the rocks, this arm increases its tension gradually by bringing small groups of fibers into play one by one as the load increases. Although all our muscles work by shortening, they don't all produce movement. This fighter's muscles are not moving at all. They are using their contractions to resist movement.
Chuck him off, Ben!
And when the muscles do move, the same movement can conceal a very different amount of force. To take aim, the fighter uses just enough muscle fibers to move the weight of an arm. But when he breaks the block of wood, he uses thousands of extra fibers to add many pounds of force to the same movement. So far, all the activities we've seen have depended on voluntary muscles, which we control with our conscious minds. Most of these muscles lead an unpredictable life, ready to leap into action when we need them. But there are places in the body where movement and force are needed all the time in a very predictable way. With breathing, for example, the diaphragm muscles move in and out automatically to keep air flowing through the lungs. But when we need to override the system, which happens when we take a deeper breath, we can still move the muscle voluntarily. And human speech couldn't take place without a mixture of voluntary and involuntary muscle actions to coordinate our vocal cords, tongue, and cheeks. But many muscles in the body are totally beyond our voluntary control. The circulation of the blood depends on movement in the heart and blood vessels. The digestive system is always active. Urine is constantly being formed and stored in the muscular bladder. All of these activities use a different type of muscle that can do a lot on its own. Muscle cells are at their most independent in the heart. even a single heart muscle cell can beat on its own until it runs out of food or oxygen. When it's in contact with another, the two will beat time together, sharing a common rhythm. And when a whole collection of heart muscle cells are in contact, they can start to generate regular pulses of force. Another type of involuntary muscle forms the lining of the digestive tract. This moves restlessly day and night, a conveyor belt carrying a never-ending series of waves of contractions. This smooth muscle, as it's called, carries out regular squeezing movements all on its own whenever it senses the pressure of food. Two bands of muscles, one along the intestine and one in rings around it, work together to produce this rhythmic rippling called peristalsis. In the blood vessels, there's more smooth muscle at work. They're not just passive tubes, but take an active role in keeping the blood pressure at the right level. In the walls of the arteries, there are bands of muscles that are always tense. If the pressure drops in some part of the system, the muscle narrows the walls of the vessels to increase it again. There are also tiny rings of muscle at certain important junctions that open and close like gates, sending blood down a particular blood vessel or diverting it away. Another type of smooth muscle plays a unique role in helping us urinate, or rather in helping us not urinate until we're ready to. This film shows events inside a living human being as he prepares to urinate. The bladder here is lined with a special type of smooth muscle, and as the bladder reaches a certain size, it sends nerve signals to the brain, carrying a message of mild urgency. Because these walls are very elastic, the bladder can expand a lot more as the urine trickles in before the situation gets really desperate. When we finally decide to go, we relax the muscles at the exit from the bladder, and the bladder walls can squeeze together, sending the urine rushing out.
Sit down.
The difference between the strongest and the weakest of us is impressive. You might think that some people are born stronger than others, but in fact a lot of this difference is just due to training. We are all born with a fixed number of muscle fibers, and the number stays the same throughout our lives. This is a cross-section of a child's muscle. Every circle is a muscle cell. As we grow and become stronger, the individual cells increase in size. The strongest muscles have large cells like these, and so they contain many more of the interweaving molecules that produce muscular force. At a time like this, the human body is spreading around a lot of energy in the punches and kicks of arms and legs. That energy has to be continually generated inside the body, and it comes from our food, particularly carbohydrates. Throughout the body, our muscles and organs receive regular supplies of blood, pumped by the heart and carrying many different breakdown products of our food. This blood contains glucose, which can be stored in the muscles themselves and in the liver. We dip into this store continually, and the glucose is carried off in the bloodstream to the most active muscles, where it can be burnt with the oxygen that's also carried in the blood. Like any burning, this process gives off heat, and that's why we get hot when we're physically active. In fact, it can be the most important way of keeping warm when it's cold. Here, by a special optical technique, we can see how air around the arm is heated by contact with skin and muscle. Contracting the thigh muscles to bend like this produces a visible increase in temperature, as this thermographic image shows. The more heat is radiated from the leg, the redder the image, as you can see in the thigh. Increased activity means deeper breaths are needed to supply oxygen for the burning in the muscles. Sometimes we're so active that we need more oxygen than our lungs can supply. Then the body has a way of borrowing oxygen from internal stores for a short while. But that oxygen eventually has to be paid back. That's why we breathe heavily or pant for some time after we've stopped being active. Gradually, breathing returns to normal as the fresh supplies of oxygen finish paying back the oxygen debt and supply the normal bodily needs again. Of course, providing brute strength is only one task carried out by our voluntary muscle cells. Even in the area of the face and head alone, there are many small, delicate muscles that help us to stay alive and at the same time to show the more sensitive sides of our human nature. Lips help us eat and kiss. Jaw muscles can crack nuts with a force of 180 pounds and also help us speak. The neck muscles exert a gentle tension to support the head and help us say yes or no with a nod or a shake. And in and around the eyes are muscles that point them in the right direction, adjust for the right amount of light, and even seem to express our emotions. In fact, only mammals have facial muscles at all. None of the lower animals can frown, snarl, suck, kiss, or smile. And only humans can laugh. All the body's skills depend on the remarkable properties of muscle. Any human designer might find it a daunting task to create a device that's capable of all the activities of muscle. The design of these versatile cells allows millions of them to work together to lift hundreds of pounds or to squeeze tiny amounts of blood through the capillaries. And they can act quickly or slowly. Tiny muscles in the eye react with lightning speed. Others in the intestine are sluggish and slow to respond. When the whole body has to move, the effort is shared among many muscles widely dispersed throughout the body. They provide the power for an intricate collaboration between smoothly turning bone and joints, and the complex control systems of the brain and spinal cord.
Oh! Oi, what's your game?